Good afternoon, everyone, and welcome back to the session. As part of our masterclass sessions, we are trying to understand the entire tech stack that is involved in building a successful production level data science solution. And as part of today's masterclass, we will be talking predominantly about how the data pipelines are going to be an integral and very, very important part of developing a production level analytics solution. And as part of today's session, we will be trying and understanding the terminologies like ETL. Of course, we'll start with data pipeline. Then we'll talk about ETL, ELT. Then we'll talk about warehouse. We'll talk about data lakes. Then we also have something called as lakehouse. Of course, we'll not be dealing with the hands-on in this particular session with respect to these tools. But yeah, the infrastructure, understanding of this infrastructure and roles of these infrastructures in various scenarios are something that we will try and understand. Then we'll also try and understand how important a CI/CD and CT are important for us to develop a machine learning model. I'll write ML, an ML model at production level. And as part of this, we will also talk about various validity steps that we will have to talk about, or I should say validation. Let me rephrase that. Different validations steps that we will have to talk about. So this is the overview. And finally, we will also try and look at Git and GitHub concepts. We will try and I'll also try and demonstrate how we will use GitHub for doing a CI/CD related implementation, how the code repository can be utilized to ensure that the models are constantly being trained. This part specifically falls under the 6th step of CRISP-MLQ. Who remembers the 6th step of CRISP-MLQ methodology, which is the standard methodology for data analytics projects? CRISP-MLQ, 6th step. Let's see how many of you have mentioned. Only 3-4 people. What happened, guys? Everyone? It is monitoring and maintenance. Right? And of course, part of deployment also will be something that we will be trying to understand here, CDCI and CD. So these are the concepts that we will try and understand. And as I said, GitHub is something that we will also learn. And this is going to be very important for everybody. All of you must try and understand the GitHub usage. All right. So as part of the data science curriculum, we try to understand the various terminologies here. Right, you all people understand the onion peel diagram here. This is the standard diagram that we use. And the end result that we are trying to achieve is AI, where we are trying to ensure that a machine can mimic a human behavior, a biological brain behavior, right? The human brain. This is the end result that we try to achieve. Data science is the R&D department or R&D area, research area, which will also try and help us to understand where the problem is and what the problem is, the reasons for this problem, and it also allows us to identify the best possible solution to address that particular problem. By doing experimentations, we will be able to try and find the best solution. In order to do this research, we need techniques. Those techniques are called as your data mining techniques. This is quantified, or I should say statistical methods that we will use. Stats and maths based techniques that we will use. It's a process basically which allows us to process the data. The data mining comes under, right? Comes with different techniques, different approaches. We have machine learning. Machine learning is applied in order to identify the pattern, hidden pattern in the data. We may have labeled data or unlabeled data. If you have labeled data, then we will be doing predictive analytics using this concept, where we are trying to represent the business problem on a mathematical front. And if I can achieve this function, which represents the condition, business condition, that is nothing but the relation between the factors and the outcome, then using that, we will be able to do predictions. But in order to do that, we need to have the labeled data. We can also do descriptive analytics. This is where we will not have labeled data. We just have data. But in order to do this, our data should be in structured format. If your data is in structured format, then we call this approach as machine learning, where we train our algorithm, our machine, in order to bring up this equation. Then we also have deep learning, which is kind of a branch of machine learning, which deals with unstructured data. So our data would be unstructured. We will try and convert that into structured format. There are various strategies that we'll have to apply to ensure that the data comes into the structured format, and then we'll apply the y is equals to f of x kind of a logic. Right? So this is your deep learning. Now, why we are trying to do all these different steps? Now, in any business we talk about, the first thing is we want to try and understand what we have done till now. And to do that, we use data analysts capabilities, or basically we use these techniques to generate reports, right? We call these people as data analysts. We get reports, right? And we use business intelligence tools. This is descriptive analytics. We are looking at past. Then we try to use these mathematical techniques. We call them as machine learning techniques. And this will allow us to do the predicting the future by using the mathematical equation that we were just talking about, which is represented as y is equals to f of x. The function is basically talking about or defining the relationship between y and x. Then we talk about the data science logic, which allows us to do this, creating a new future. Now, what exactly this means? I will have this mathematical equation generated, right? So if I have to explain this, y is equals to, let's say, a x1, b x2, b c x3, plus so on and so forth. We will try and write this mathematical equation. Now, in our data set, if I try to draw a data set, I would have multiple fields like this. Let's say this is x1, this is x2, x3, so on and so forth. And we also have labeled data is there. Class, or we call it as labeled, so labeled data. Okay. Now, when we get this equation, when we are getting this equation, we are trying to substitute these values x1, x2, x3, so on and so forth, and then calculate the y, the predicted result. right? We're trying to get this predicted result. Now, when we try to use this mathematical equation, we will also come to know on what should be the appropriate x1, x2, x3 values, which gives us the best possible outcome that we are seeking. We'll come to know, right? So this will allow us to define what input parameters we should pass to get the desired output. So we are controlling the future. We are defining what factors should be maintained so that we get our desired result. Among so many different solutions, we will say this is the best solution. So that means we are creating the desired results by controlling it, thanks to this equation. So we are looking at the past, understanding the pattern, understanding the relation between the factors, and then trying to use techniques which can allow us to build, do the prediction by building the mathematical equations. And among all the different possible solutions, we will try and pick one mathematical equation which gives us the desired result, the best results. And using that equation, we will also be able to understand what factors should be given in future to get the desired outcome. Right? So data science is all about giving the solution. We also call here this as prescriptive analytics. Prescriptive analytics. Right? And then this is exploring all the futures. So after understanding multiple options, we will try to automate it. So we're saying, hey system, you do everything and find the best solution and then implement it. We're automating the process. Right? So these are the various phases of our solution that we're developing with respect to the business problem. All right. Now, once we have understood this entire paradigm, we talked about this crisp MLQ 6 steps, right? Just now we talked about the sixth step. But we also have the initial steps, of course, right? Only then we'll come to the sixth step. So here we are talking about the 6 standard process that we will have to follow. And let me tell you, the process that we're talking about involves the business aspects and the technical aspects both. When I say business aspects, understanding the business, trying to logically understand whether the data that we are seeking or using or generating is logically correct or not, right? So that basically this is logical or business, you can say. And there is also technical capabilities that are required. Okay. The first step is generally where we gather the requirements. And when we talk about requirements, we are trying to understand the business in the first place and what kind of data that is getting generated by the business, whether it is generated in the first place or not. If yes, what kind of data it is generating, what conditions it has. And then we also try and examine what tools and techniques are being used, right? Resources and everything. So a lot of things are gathered, planned here. This is a logical step, right? Because we will be doing a lot of planning at this stage. You'll get your senior management people involved in this. You'll have technical team involved in this, architectures, the subject matter experts with respect to the functional capabilities, the business capabilities, right? So all those people will be involved in this particular first stage. Now, once we do gather all the requirements, we try and understand the current conditions, the business conditions, the technical resources that we require, hardware, software requirements that we basically will have. All the requirements are gathered. Then comes a step where we actually kickstart implementing the solution. And this is basically where your data engineers come into the picture. The job role that we are talking about here is generally handled by the people so-called data engineers today. Now, what is this step here, right? What is the primary step here? We are talking about dealing with data. So we will have data collection and data manipulation. Manipulation, you can say data pre-processing, cleaning, organizing, right? All those things part of the data manipulation itself. Now, when I say data collection, we need to always understand the data sources, right? So everything boils down here, friends, data sources. In all our classes, we talk about right, dealing with data, but where is the data getting generated from? Where is it getting stored? Is it getting stored in the first place or not? Can we access that software? What kind of software that is being used by the organization, right? What are the technical capabilities that we have or our team has with respect to dealing with those softwares? So all these are the details that we will gather in the first phase. Now, for example, the most popular and most widely used software is RDBMS software in our businesses. This is the software where the data gets stored. How is it getting stored? Not in file format, but in tables format. They're only worried about data, not the files in which the data is stored. Right? So it's not like you open an Excel file and write entire data and store it in your hard disk. It's not like that. The software will take the data, the content which is there in the file, and store that in a table format. And one thing we need to remember is the structure. RDBMS data will always have structured data, right? Because it is always organized in a table. And also there is this keyword called schema, which is basically the data definition of your enter data. So this is the definition of your table. What is the table name? How many columns will it have? What data will have in each column, right? All that definition will always be upfront defined in RDBMS software. This is our source. Now, as a data scientist, as a person who's familiar with machine learning capabilities or deep learning capabilities, where you're trying to primarily focus on developing an AI solution, your primary skills are to have the understanding of the business, understanding of your ML methods, algorithms, which are based on maths and stats, and a little bit of Python skills so that you can manipulate the data and apply these algorithms in Python on your data. Primarily, these are the requirements for a machine learning expert, a data scientist. But in order to do this ML algorithms, right, understand the data with respect to the business conditions and all that, we need data first, right? So as a data scientist, you'll also have to now look at where the data is coming from. Data is there here. So you need the data to start all this work. Okay, that is important. But where is this data stored? How can I get that data? So if it is an RDBMS software, then you should be familiar with SQL programming skills, SQL skills. But you're not a programmer, you're not a SQL developer, you're not a database developer, right? You don't know about RDBMS. Your primary focus is your subject, that is your functional knowledge, the domain knowledge, understanding of the data and all that. You're not a software programmer. So this is where we will have, or this created the demand for people who have the skills who can deal with these kind of systems. Right? And we call these people as data engineers in today's world. So even before the data scientists can do machine learning algorithms, data engineers should get involved. Now, these data engineers will ensure that the data is getting made available to data scientists. Once the data is available, then data scientists can do anything. But where is the data coming from? Right? Somebody has to give them, right? Somebody should ensure that data scientists are provided with the data. Okay, so that's the role of data engineers. In previous times, in old times, this specific task was called as ETL. The full form of ETL is extract, transform, and load. Okay, extract, transform, and load. We will discuss more about this, but ultimately we are trying to extract the data from different systems. Then we will try to transform it into a specific format and then load it into the system so that data scientists can do whatever the task that they are supposed to do. That is your machine learning step, this part. Now I've just given one example where the source could be your SQL, right? RDBMS software. Now, if you're familiar with the libraries, the skills of the softwares and all that, then using Python, we can connect and then get the data. Okay, that is the first integration. So we're talking about integration between the source and the processing tool of your data. So this is RDBMS. That is nothing but SQL based software. Plus this is Python in today's world. So connectivity should be established between these two so that we get the data. Once the data is collected, then we can also use data scientists to do their magic, the data pre-processing and all that. Okay, that's the first rule. In this 6 phases step, the first role is predominantly a technical role where we get data engineers. Then we will have the data scientists who perform the data mining techniques. They try and manipulate the data and then get the mathematical equation. We try to evaluate, of course, we'll have to tune and evaluate. That's not evaluation and tuning. We first tune and then finally we will evaluate and get the best solution, the final result. The best model will be identified. Now, when I say best model, always remember, as a data scientist also, our primary objective is to build a solution which solves the business problem, not the problem in the data that we are working with. The data is just a sample which represents that condition. It may not be exactly replicate the condition. So we should not focus on developing a solution only for that sample data. We should focus our energies in developing a model which is more generic in nature, which can solve the business problem using the sample data. Okay, that is the best solution that we will have to find out. And in order to do that, there are different evaluation techniques that we will have to apply to ensure that the model that we developed is giving a solution in a more generic way. Now, once this best solution is identified, Data scientists will identify the best model. Now, once this is done, they will try to save this particular best model. We will save it. Ultimately, it's a software that we are developing, right? It's a code. So we will try and save the best model. Now, this saved model should be actually integrated into the infrastructure of the customers, because customers are already doing business, right? They will have some infrastructure, some application. So the solution that we are developing should get merged or should get integrated into their current environment. So that means, again, technically, we need to try and integrate that solution, the saved model, the software. And for that, we need specialists who can actually do that. As a data scientist, remember, we are not programmers. So we may not be able to completely integrate this model or the saved model into the application that client is already using. Because when you say the existing application, there could be different kind of a UI. And then in the backend, there could be different kind of databases, right? And they probably will be deployed in different systems. So a lot of these technical and right, especially software and hardware related things that we speak about will get involved. Now, again, as a data scientist, our focus is only to develop a machine learning model. So who do we need here? We need people, right? Software developers. These people will do the integration of your machine learning into the existing infrastructure. Okay. In the software world, in the industry, not just in software industry, in basically the industry, this particular role is called as DevOps. So we're speaking about development of a solution, that is your software development, and then operationalizing that particular solution. Operationalizing means after you develop, it has to be used, right? You need to ensure that the development is being used. So we need to operationalize the solution. So that's where we say DevOps, Dev plus Ops. Now, if I say that development is not any software application, but rather the machine learning, specifically machine learning models, then we call this as machine learning operations, ML Ops. This is the role and responsibility of the ML Ops, where we basically deploy the solution. But when you're deploying the solution, one thing that we need to remember is we should not deploy a solution which is a one-off kind of a model. One-off models cannot be used. What does this one-off models actually mean is, practically what happens is, we'll have a business problem. This is my business conditions or business area. This is represented by the full data set. We call it as population. In order to deal with this, we will have to get data. Now, this data will never be the full data. It will always be a subset. We call this as sample data. Right? Whatever the data that you get, it is always a representation. So we will call it as sample data. Using the sample data, we will try and develop machine learning model. Okay, ML models are developed. This is what we do, right? ML models are developed. And once the ML model is developed, we say, hey, this is the best solution. You go ahead and use it. This is what we are doing, right? How many of you have actually worked on projects, at least one project? You might want to raise your hand. People who are connected here. How many of you have worked on project or currently working? Or how many of you have actually completed your assignments? Yeah, that's okay. At least one. Machine learning assignments, anyone? Predictions, your regressions, classification, unsupervised learning techniques. Assignments, at least. Okay. So let me try and ask you people a simple question. People who have completed the assignments at least, right? With respect to machine learning. The machine learning problem statement is basically given, and you will be given a data set. Let us assume this data set contains, let's say 5,000 records and 10 columns. Okay, this is the data set size. So what you do, you understand the problem statement, you look at the data, and you understand what algorithm you'll have to apply. Because assignments, obviously, it's very easy. For a specific algorithm that you're learning, you have this question given, right? So you'll basically know what algorithm you'll have to use. So what is the approach? What we do? In order to solve this problem, you will have to use CRISP MLQ methodology. As part of this, once the objective is identified, the first step is objective or objectives. Then also draft the constraints. Okay, we'll understand this. Post this, the data set is already given. So we are going to import the data set into Python. And then what we do? Data pre-processing. So we will perform EDA, we will also do visualizations, we will also do various cleaning tasks on this particular data set. Now let us assume the data set that we have contains missing values. So if you have missing values, what we do? We try and develop a method for imputing them. So we do imputation. Okay. So let us assume it contains a column which is non-numeric. So we will do dummy variable creation. Okay, scaling is also something that you do. Assume you're also doing scaling, standardization or normalization. You're doing. Right, and data is ready. Then fifth step, once the data is ready, after all these different things that we do, cleaning, organizing, EDA. EDA includes visualization as well. So once we do all this, the data is ready. And here we do data partitioning. After doing the data partitioning, we'll apply machine learning model on the training data. We try and tune the model by altering the hyper parameters. Right? We are basically trying to clean the model, beautify and improve the performance of the model. Okay. So that is done by altering these hyperparameters. We call this as tuning process. And once we identify the best solution on the trained data set, right? We further may be splitting this into train and validation, and then we'll validate the best solution here. I'll write it here. Okay, I'm writing in reverse order. So I'll write 7 here. Now, once we find the best solution here, we will evaluate it on test data set. Right? We will evaluate on test data set. This will tell us whether the solution is good or not. Let us assume that we found the best ML model. Once this is done, our job is done. Assignments, right? This is what we practically do. But what additionally you people have to do? This is something that you need to understand, friends. What additionally you people have to do? Let's see if I have any messages. Okay, great computation. Wonderful. What we generally don't do is the model that we are developing here, right? We are calling this as best model. The model that we are getting is only trained on training data set. But the idea is to have the model which can predict the future. For unknown data, it has to work, right? The prediction has to be done when you don't have a output variable, right? It is the model is not designed or not being developed to work well on test data. Okay, this is only to evaluate, that's all. So what we have to actually do is combine the test data and train data. That means we go back to the historical data and then retrain the ML model, which is defined as the best model, on the 100% of the data. Okay. Take the 100% data and retrain the model. And that will be your final model, which needs to be deployed. Deployed is nothing but operationalizing it, right? It's basically being used for predicting the new data. Okay, this is one step which we don't do, right? We will have to do this. The next step, even in assignments, right? We do. I'm sure nobody has done this. Very few do, right? Very few of you people do this. Now, once this is done, what we have to do is when the new data is coming, when predictions are coming in, to be done, right? The new data is coming in. Will you directly pass this new data to the ML model that we have developed here? The best ML model for predictions? No, we don't do this directly because you have some of these pre-processing steps to be done. Okay. This is called as pipelining. So the new data which comes in, it has to go through all the process that we have done here for the data. It has to be verified for missing values. If missing values are there, then you'll have to go do imputation. If you have non-numeric data in new data also, when you get right, it will be in the same format. So your dummy variables have to be created, right? And then the new data that we are getting is on the original scale. We transform it to have the scaled data, right? After doing all that manipulations, the manipulated data will go as input into the model. Okay, not the raw format. So this sequence of steps that we are trying to implement here are called as pipeline. This pipeline has to be designed for your new data as well, or any data that we are going to use for this model. Now, another question is, here we have done bunch of data pre-processing steps. Let's say 3 steps we have done here, right? Missing value treatment, dummy variables, and scaling. What if in this new data, I have outliers? Should I not check for the outliers? Just because your previous data does not have outliers, does that mean that here we should not have outlier check when the new data is coming in? Will you know that the new data which is getting generated will not have outliers? It will have only these problems that you have seen in the sample data. What do you think? Can I have outliers in new data or not? I may have, right? Exactly. I may have duplicates, for example. We will not know what conditions will be there on the new data. So what is that we have to do here for new data? We need to ensure that, let me change the color. We need to verify all the conditions. All the conditions have to be verified for new data. And based on the verification, pre-processing steps have to be implemented. So in the pipeline that we are designing here, right, we're talking about pipeline, right? This pipeline should be designed in such a way that all the conditions are automatically verified on any new data that we are getting. So it is more like an automation that we are trying to do. Okay. So the pipeline should be designed to verify all the conditions. And the data which is getting generated, which is getting stored in the source, should pass through the sequence of steps that we are defining in the pipeline before it goes into the model for predictions. Okay. These steps are very important, and this is the reason why we are emphasizing you people to look at the EDA steps very, very, very detailed. EDA data pre-processing steps are very, very important. And this is a laborious job because it has to be performed on each variable at a time. We call it as univariate analysis. So there are certain libraries which are developed to ensure that this process is, at least some part of it is automated. And we call this as auto EDA libraries, right? In Python, we have auto EDA libraries which can be utilized in order to ensure that all the verifications are completed. Okay. So this is something that we don't do when we are developing a machine learning model on sample data. But when you are doing it on production environment, when it has to be deployed so that the new data is being used for predictions, then we need to do all these verifications. Along with this, there are a few other things that we will have to do, right? I'll come back to this stage. Let me erase this part. I'll try and write the steps that we need to perform here, which are also not being discussed, right? As part of your regular machine learning model development, we don't discuss this because our focus would be on understanding the algorithm and trying to understand how the algorithm works on a given data set, what kind of results it gives, right? Our focus would be on those parts, not on the implementation part, right? So we'll focus, we are trying to focus on those aspects here. So 11th step, this is one of the steps that we will have to do when you're developing the machine learning model, is even before the model, best model is done. right, is, let me change this number, right, some number, okay, at the initial stage before the data, let's say third step. Once we get the data, right, second step is data collection. So third step is data validity. Here we are also doing versioning. Data versioning is collected. We are trying to understand what kind of bias will the data have, right? Whether the data has imbalance or not, bias or imbalance fields is something that we're also trying to record. Data definitions from the business perspective, data types from programming perspective, computers, right, or technical aspects perspective. All these are something that we will have to right, validate. Now, when you're trying to collect the data, right, we may get the first version 1 of your data is obtained. You may get, let's say, 2000 observations with, let's say, 30 columns. We try to get everything that we have in the data set. So this becomes your version 1. Now we do analyze this data. We'll try to understand the properties and all that. And when we do that, probably we'll get to know more details about the business, and we will take version 2 data from the, again, the business. Maybe this time I get 3000 rows and 15 columns, or maybe only 9 columns. There will be some of the columns repeated. There may be some columns, new columns that we are getting, right? So on and so forth. Okay, this could be one of the scenario. What is the properties of this data, and what are the properties of this data have to be recorded for doing the comparison? Okay, for example, let's assume, I'll remove this. Let us assume we have validated all the features and we have obtained version 1, which is, let's say, 5000 records and 10 columns. Okay, this is the finalized features. Now, in this, when you do EDA, we gather a lot of stats with respect to all the 10 columns. We are gathering all the various stats. For example, in one of these 10 columns, we have gender. And in this gender, let's say I have 70% male, 30% female. Okay, this is the first version of the data that we get. In the second version of the data, let's say I have 1000 records and I'm taking only those selected features. This is the second version. After a few days, we again get the fresh data. Now, in this second version of the data, when you again perform EDA, we get the stats and we will verify the same feature. Maybe this time I have 50% and 50% male female. So you can see the characteristics will completely vary from this version to this version. Now imagine this version is your training data. This version is your tester data, assume. So you can clearly see that there is a difference in your training data set and test data set, which will also show the difference in the machine learning models performance on both these data. So we are recording all the stats for all the data sets that we are basically working on. This is data versioning. We will use this to validate whether the data characteristics are consistent or not. So, for example, if I have to talk about different data sets that we will typically work on, will be this. So you will get historical data. Okay, this is set 1. We are going to split this into train, validate, and test data. Along with this, new data will also be there. So you will have 1, 2, 3, 4 different variations of the data set that we will have. And these 3 typically are part of your historical data. So partitioning is also something that we will have to validate. Again, this is something that we don't do. Do we? No, right? I mean, you can be very true to yourself. Probably you might have done validity only with respect to the label data. But what about the input factors? Did we validate input factors? Did we compare the characteristics of the input factors? No, we did not do that. This is also something that we will have to do if you are trying to deploy your model. Okay, production level, when we are trying to develop, all these things have to be verified. Okay, there are a bunch of other things which, of course, will come into the picture. We will talk about all of that. But these are some of the steps that we will have to do, friends, which eventually we don't do. And along with this, right, at the final stage, if I have to say, when you recorded all this, right, you will be able to identify the data drift and the model's drift. So how is the model working here? How is the model working here? How is the model working here? And how is the model working on the new data? Are the characteristics in these data sets are different? If you are looking at the new data, this will be the final data. Right? So do we have any drift changes in this new data set? We'll record them. Right? What are those changes and all that? We will have to highlight that. Okay, and then we'll also have model drift. With respect to the data changes, model will also change. So how is that change coming in the picture? This is basically part of your, this job that we are doing, talking about here is the part of maintenance and monitoring. At production level, these things are called as CI, CD. And if I speak about machine learning operations, then we basically talk about continuous training as well. So integration, continuous integration should be there so that the new data that is getting generated will flow into the system. That's your continuous integration. And continuous development is basically means the training, the pre-processing, right? All that. This is basically part of your continuous training of your algorithm. Keep training it, keep predicting, keep training, keep predicting. So continuously the process has to be. So this implementation needs to be there as part of your Pyspark queue. The queue is something that is not recorded here. That's because when we try to implement the solution, a machine learning solution on a sample data, which is what we generally do, we only try to build a POC. POC is nothing but proof of concept. So the algorithm that we are developing will be specifically built on that particular sample data set. And we validate whether it works on the sample data or not. That's all. And we don't try to look at the quality aspects when we are doing this POC. The CRISP ML queue basically emphasizes that the solution that we are developing would actually work as expected on the new case as well, new data scenario as well. And to do that, we have to implement the quality aspects. Okay, that's where your data validity steps are coming into the picture. In your business and data understanding, we are trying to implement these steps along with your success criteria, benchmarking things, right? All are the part of the quality aspects. Okay, so we are basically talking about the steps that have to be focused before the machine learning model is developed and decided, the best model is decided, and after that steps are done, before and after. Okay, so a data scientist should be capable of all these different things. Of course, in the industry, practically, we will have data engineers. The jobs are segregated and we will have specialists to do this job. Data engineers will be there. Machine learning and deep learning engineers will be there here, and MLOps will be there. Okay. Previously, we did not have all this. We had data scientists plus operations team. But now, more production implementation is being emphasized, and hence we'll have these specialists coming here. All right. So this is this is basically your entire process, friends. Hope you understood the gist, right? So we're not just focusing on these 6 steps. When we talk about these 6 steps, there are many aspects that we'll have to look at when we want to productionize this. So as you can see, this diagram is showing a typical data flow, how the data flows from source to destination. Source could be anything. There could be multiple sources, in fact, where the data is getting recorded, the relevant data is getting recorded. So we will collect all the data, do the pre-processing, and then try to consume it. So as part of our discussion, we try to highlight the comparison, the roles and responsibility of data scientists and data engineers to begin with. So as a data scientist, we try to have statistical programming capabilities, machine learning capabilities, analytical approach, that is business thinking and all that should be there. Logical thinking should be there, right? And our primary focus is to look at the data and try and understand what is happening in the business. And as part of the skill sets, we are primarily expected to look at the data and then bring the right questions and also try and find out solutions for that. And in order to do this, of course, we need to have machine learning, data mining, statistical, and a little bit of big data infrastructure skills. And of course, Python is one of this integral part of your data scientist. Now, coming to the data engineers are expected to be the bridge between the data scientists and the data. So we data engineers will ensure that the data is made available for data scientists. And the primary focus of data engineers is to ensure that the multiple softwares that we are using in the entire organization's infrastructure that we are talking about, tech stack that we're talking about, we will ensure that all these different softwares are integrated to ensure that we have a logical data flow designed. We call this as pipelines. So we are designing, building, and integrating the various systems to ensure that the data is flowing from one system to another system. So we're ensuring that the data is available. This job is called as ETL process, where E stands for extract, T stands for transform, and L stands for load. ETL job is implemented. So this is the comparison between data scientists and data engineers. We'll take a short break now, and then we'll come back. 10 minutes break, and then we'll continue our discussion. So friends, a quick recap. We talked about the CRISP MLQ methodology that we generally follow to implement a data analytics or machine learning solution can be broadly segregated into 3 areas. One is data engineering area, Then we have machine learning or deep learning area. And then we also have ML ops area. Data engineering basically deals with the different systems, and we try to ensure that data pipelines are designed so that the data comes from source to Python for machine learning implementation. When we talk about source, there could be many sources from which the data needs to be collected. So we typically talk about ETL roles. Then we know machine learning role. And finally, we have machine learning operations role, where we try to deploy, we try to maintain and monitor. So this can be broadly segregated into machine learning development and then operationalizing, deploying the solution on the production environment so that the end users can start using it. So these are the three different segregations that we discussed about. We also talked about data validity. Data versioning. Right, and we try to practically see how many various steps that we will have to implement. We zeroed into 12 or 13 different steps. It's not just a typical POC that we develop when we talk about machine learning algorithm. And this is what we have been doing all this while. But when we talk about developing an analytical solution, we will have to keep in mind that the best model we're coming up with should actually be used for new data. But this model that we're developing will be developed on a small subset of sample data, right? And the conditions, the characteristics of sample data may be completely different from the new data, right? So the solution that we are developing should be generalized to solve the business problem, not the data that we are having. Okay, that was something that we discussed in now. Let us emphasize on talking about pipeline, implementation of data pipelines. When we look at a data pipeline, it is nothing but a series of steps. Data pipelining is basically a series of steps which will involve integrating, right? That is basically we are trying to connect two different softwares or multiple different softwares so that they can communicate between each other in such a way that the data which is basically is part of those systems, right? The data that is being held by these systems can move from one system to another system. Right? That is basically the process of data pipelining. And when we talk about data pipelines, it could be a very simple step. We are trying to move data from point A to point B, from here to here. That's all. A to B. This is something you probably would have done or already have been doing it, from, let's say, SQL database to Python. Very simple data pipelining step. But the data pipeline can be as complex as it can become, where we try to gather the data from multiple sources. And when we talk about different sources, we may get only partial information from each of these sources, which could be in different formats. So we will have to ensure that we transform everything into a consistent state, merge them, right? We combine everything. And then once the relevant data is created or obtained, we probably would have to store it for further processing. And when we try to store it, we may have to store it in different systems. So that means we will have multiple sources, and there will be a process here. And then from here, we will have to probably store it in different destinations as well. If you see here, I have different sources, the process, transformation process, and then we are trying to load. The data loading can be here, 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 right? So it could be in different places. The end usage could be different. That's what it means. Now, when you're trying to develop the data pipelines, the intention of these data pipelines is to ensure that the data is moving in this pipeline from one point to another point, right? How is that movement is also something that we'll have to define. And based on that movement, the pipelines can be broadly segregated into 3 different architectures. The first one is batch data pipeline or bulk data pipeline. We also call it as bulk data ingestion. So that means you'll have a database, for example, this is your source. I have, let's say, 1,000 records getting generated here in the entire day. One day, I get, assume 1,000 rows of data. Now I will decide a time and I'll move this entire data into different system. This is called as bulk movement. So entire data is moved from point A to point B. Bulk data ingestion. In entire one batch, we will move this. So next day we get new 1,000 records. So I have new 1,000 records in the set here. Again, I'll move from here to a complete data set, right? So that is your bulk data ingestion. The second mode is streaming data pipeline. This is live streaming data pipeline. So here we basically say that as and how the data is getting generated, the data will be moved. For example, I have 1,000 records, 1,001, 1,002, so on and so forth. So as and how this record is generated, it is moved. As and how this data is generated, this is moved. So it's like a pipeline which is open. The connection is open, and as the data is getting generated, it is flowing in. You're not accumulating here and then storing it, pushing it at one go. Data is continuously flowing. This is streaming data pipeline. Then the third one is kind of a combination of these two. We call it as change data capture, CDC pipeline. Now assume I have a stable data source where I get the data recorded. So let's assume that I have 1,000 records. We already have moved this 1,000 records here. Now in these 1,000 records, one of the transactions is getting altered, right? One of the row gets changed. Now what happens? There is inconsistency again because some values have changed here in this particular row. So CDC will ensure that the data gets refreshed with this particular change taking place here. Because ultimately there should be consistency, right? Between the two systems, the data should be same. So this implementation where we try to ensure that the data is consistently storing and having the same value is CDC pipeline. Change data capture. So ultimately, as I said, the data has to move from one point to another point. And in order to design this, we will have to understand how the data has to move. And once these requirements are identified, we will start designing your pipelines. This is another way to represent the ETL job, which is basically a typical job of a data engineer. Source. We ingest the data from all these different systems. The architecture could be any of these three. Ultimately, you'll get the raw data. We are transforming it, stabilizing it, standardizing it, and then pushing that into the destinations. Destinations could be data lakes or data warehouses. These are two different ways where we can store the data, and ultimately the consumers will consume the data from these destinations for whatever the purpose that they really require it. So this is a typical data flow. Now, when we try to design, there are certain steps that we will have to remember. These steps basically talk about what are the various tools and techniques we'll have to use to choose to design your pipelines. Ultimately, the tool that we want is something which is very easy, obviously, right? It should be easy to use. Okay, and when you say easy, it is not just from development perspective, designing the pipeline perspective, but also from a maintenance perspective. Okay, easy data replication talks about it has to be designed and developed in minimum time. So that means it should be easy and it should not have any maintenance overhead. Because when we talk about easy designing and developing, building your pipeline, that means you need to have all end-to-end steps ready. Okay? Data pipelines end-to-end that we basically should be ready. But when we try to use these end-to-end data pipelining tools to design these pipelines, these could be automated steps. Okay, and when you say easy, it is like already ready-made solution should be there, right? So that basically means what? These are more like an automated systems, the tools. But when we try to use these kind of tools, the problem is, of course, they're costly. And any customizations that you require or any troubleshooting you require, you'll not be able to easily do it. That means maintenance overhead will occur. So we need to draw a balance between these two. It should be not too complicated. At the same time, it should not be too costly. Right? You can imagine, right? Too costly means ready-made solutions. We don't want such a solution which cannot allow us to do customizations. The best tool in the industry that we can use is Python programming language, which has n number of different libraries that we can try and use. Right? Python is the best tool. It should also, the tools and techniques should also support different data sources, which of course Python does. And data reliability is another very important point. Whatever the data that is getting generated by the business has to be used as is, right? We cannot change the data. We cannot lose the data. So reliability is very important. And when we're trying to transform, we should not lose any data. Then we also talk about real-time data availability. So live streaming data capability should also be given. Okay, that's real-time data availability feature. So these are various other features that we need to ensure that the tools that we are using should have. A typical data pipeline can be defined like this. We'll have data ingestion step. And from here, we'll try to store. So when we talk about this data ingestion, right? So your data could be in a SQL database. So we're trying to bring that into a system. Now, what does this mean? I mean, this is also storage system. Here also I'm saying data storage, right? So the difference here between these two is, right here we will talk about SQL database. And here we are talking about HDFS. The difference between these two is that your SQL database is a online transactional purpose solution. That means this solution will always be busy dealing with the transactions that are happening. You cannot perform a lot of analytics on this particular database because the software is always busy with respect to handling the request for the transactions. Okay, it's called as online transaction purpose or transaction processing. What we need is the databases which support analytical processing, online analytical processing. That's basically why we are moving the data from OLTP to a typical storage space, which is called as HDFS. We can have different systems, of course. This is one of the solutions that we're talking about. The pipeline that we're talking about here is called as batch pipeline. It is not CDC pipeline or live streaming pipeline. This is a simple batch pipeline. So using Scoop, which is a command line tool, which allows us to import and export data from SQL databases into big data platforms like HDFS. So we are using that tool to migrate the data, move the data from that solution to this solution. Point A to point. Now, once the data is here, we will try to process it. Right? It could be analytics or it could be your machine learning implementation. Now, once we do this analysis, we will get the results, and those results can be showcased using business intelligence tools. This is a typical flow of your data, which generates, which basically moving from source to destination. This is a batch pipeline. Now we'll also talk about streaming pipeline. The high level, the phases of data movement will be same. The important thing that we need to observe between batch data pipeline and streaming data pipeline are the tools that are being used. So data ingestion is data ingestion, but the tool here for batch pipeline, we use SQL. Here we will use something different. We can use Kafka, we can use Flume, we can use Spark Streaming, we can use NiFi, right? So there are different tools that we can use. Then the storage. The storage can also happen in HDFS or any other softwares like this. It can have HDFS also. Then we have data processing. For processing, we use Spark. Spark Streaming can be used specifically because this is online data flow, right? So live data processing needs to be done. The Spark Streaming, Spark basically is used. So data analysis, pre-processing, and data analytics. Here also I'm using Spark Streaming, and then we will serve this in your business intelligence tools. So you can see the steps are same: data ingestion, data storage, data processing, data pre-processing, and data analysis, and finally data visualization. Now here we are trying to look at a typical flow. I will also show you another data pipeline architecture, which is a little different. We are also talking about data integration. Of course, this will be part of your previous lab steps also, data flow diagrams also, but this here we are adding. After integration only, we will get data ingestion. Once you integrate the systems, you'll be able to ingest the data, right? So this step was not defined in the previous case, but it is always an integral part. So let us say data ingestion is being done here. Streaming again. So I can use Kafka, and then data processing, then data storage, and then data analysis, and then finally serving. If you observe, there is a small difference between the two data pipelines that we spoke about. The difference is that here we are doing the pre-processing first and then storing. Whereas if I go back to the previous one, we are doing the storage first and then pre-processing. Right? These two steps are changed. So what we are doing here, we are typically, right? We are typically doing a ETL process here. Extract, transform, load. In the previous case, we were doing ELT. Extract, store, and then pre-process. Look at that. Extract, pre-process, right? So let me write it here. This is E, extract, load the data, storage it, and then you transform it when you want to use. So ETL, ELT, that's the difference. So small change on how you are dealing with your raw data, whether you're transforming it and then loading or loading and then transforming, right? So these are the typical two different solutions that we see. And when we talk about data sources, these are different solutions that we have. So database softwares are even today heavily used. And among the database softwares, the relational database management systems are the most happening softwares that we use in the industry today. And the RDBMS systems will always use structured data. So we have databases, flat files, cloud platforms, various web services. You also have the social media platforms, the threads, the blogs, survey data, right? All these things will become your other sources, and RSS feeds also are part of your data sources. A typical pipeline, right? So from point A to point B, your data is already there in database softwares. Then we will try to connect to this softwares and collect the relevant data. So you can see these are different codes, right? Different softwares that we have. MySQL DB, this is an RDBMS. PostgreSQL, you can call it as RDBMS. Microsoft SQL Server, this is also an RDBMS. Whereas MongoDB, this is your NoSQL database. Right? Whether it is SQL database or NoSQL database, we will have Python libraries which can be used to directly connect to these database softwares and then get the relevant data. All you need to have is something called as connect string. Any database that you talk about, right? You need to have a connection string. A connection string is combination of the host name or the service name, the name of your database basically, which can be identified over internet for connectivity. So it could be host name, that is your computer name where the software is installed, or the service name itself, the database is designed as a service, colon, port number. And once we have this address, we will need to have the credentials. Credentials are username and password. All these together are called as connection string. So you need to have the database details, the host name or the service name. Then you need to have access to that particular database to get the data. Any database, right? So this is something that you should have. Once you have it, you'll be able to directly connect to the database from a remote location as well, and then try to get the data that you require. Now, let me talk about the differences between data warehouses and data lakes. If I go back here, yeah, typically if you look at this, we talked about this one is ETL. The previous slides that we have seen is ELT. So here we are storing first. Here we are processing first. Processing and storing. That means the data here will be in an organized fashion, structured fashion, right? Processing and storing. Whereas here, directly you are organizing the data, right? I mean, your data is in a specific order because you're pre-processing it. Whereas here we are saying store it first and then required you pre-process it. So here, the data can be unorganized, unstructured. Okay, so these are very important points that we need to remember. And this is where your destination changes, because ultimately you're talking about storage, right? You have to store ultimately. So that means your destination will vary with respect to the capabilities that these software should have. Organized data, unorganized data, right? So to support the ETL and ELT flows, we have the data warehouses and data lakes as your destinations. Data warehouses are nothing but online analytical processing softwares. You can imagine data warehouses as large-scale database softwares, which are specifically used for doing all these analytical related processing. So you'll always have structured data. Data lakes are just like folders where you are putting your data. So you can put any kind of data in that particular folders, semi-structured, structured, or unstructured. Your data can be big data also when we want to try and store the data. Right? You can also have regular size data for data warehouses. It doesn't matter, right? So it's really not a big problem even if you have regular data. The cost factors are not varying too much with respect to your OLAP and OLTP. So you can also store regular size data for your analytics purposes in the data warehouse event. In the data lakes, we only use this when we have very large data. For regular data, we really don't need this, right? So everything can be organized and stored. Okay, so generally when you have very large data, we use database, right? Data warehouse softwares will basically have organized data. That means your data should have specific predefined structure or definition. I mean, schemas are already available in warehouse. We're processing, transforming, right? So that's something that we need to understand with respect to data warehouses. Data lakes are just like folders, dumping yards. We create folders and store the data there. It could be in different formats. So schema is not mandatory, but when you want to read the data and create a structure, then yes, we will be able to do that. Hence, we call this particular characteristic as schema on read. Okay, data lakes, we basically talk about schema on read. Data warehouses are going to be an expensive solution, whereas here we have cost-effective solution. The cost associated with data lakes per GB storage is very less compared to data warehouses. So cost factors are also involved typically to decide whether you should go with data warehouses or whether you should go with data lakes. Generally, your operational users, operations team will use the data warehouse. They need to generate some reports and all that, right? So the data should be in organized fashion. So operational team will generally use data warehouses. Data lakes basically are the dumping yards for the entire raw data that gets generated. And this is where data scientists will show their interest because they can explore a lot of things on this data that we are going to get. Right? And as I already explained, the process is defining should we on what software should we be using, data warehouses or data lakes. So extract, transform, and load. That means your data is in organized fashion. So we typically go with data warehouse. Schema will be defined here when you're trying to do transformations. Whereas extract, load, and transform, here we are dumping the data into the folder. We just load it. We don't transform it. Transform comes later. So here, data lakes. As I said, we will have predefined reports that we might want to generate on this particular data. But here, we will be able to do R&D. Raw data, right? So research and development can be done on this particular data lake source. These are some of the examples you can follow. The Redshift, BigQuery, Synapse Analytics, and DB2 Warehouse. Right? So these are the popular names, especially BigQuery is kind of very popular among the circuit with respect to data warehouse softwares. On the cloud platforms, BigQuery is very popular. When we talk about data lakes, these are nothing but space where you just dump everything, right? So you'll have HDFS file system. This is a typical offline Hadoop cluster storage space. It could be on-premise or local server also, but it is a cluster storage space. Big data can be stored. We have S3 bucket. We have Azure Data Lake Store, GCS. So these are the typical comparison between data lakes and data warehouses. Now let us talk about data architectures. We talked about data flow diagrams, we talked about data pipelines, we talked about variations in the pipelines and all that. And when we talk about data architecture, there are some standard data flows that we typically see, right? The designs of how the data is flowing from one system to another system. There are certain standard flows. So we are basically talking about these steps, standard steps as data architectures. Nothing but data pipelines. We have specifically following certain data pipeline steps, then it becomes an architecture. So we are designing this data pipeline or data architecture at the planning phase. And this allows us to define what systems we should use, what standards we are using to maintain, right? What softwares we will be typically have to integrate, right? Whether the pipeline that we are designing, the business requirements and the pipeline that we are designing, which is batch mode or CDC mode or live streaming pipelines, right? Whether these are required or some other alternatives are required. So all these are part of your planning phase. Okay, and these data architectural diagrams or architecture will allow us to understand how the data is getting processed, stored, and utilized in an organization. And then we will basically, if I talk about this, right? Yeah. So the data processing, the operations that we basically use for doing the processing, pre-processing, can be upfront designed or defined. This will ensure that the entire development of your data flow or data architecture becomes easy. We will be able to understand from where the data is flowing and how the data is being consumed. Right, so from storage systems, from data processing systems, right? Then we'll also talk about planning phase. So data architecture diagram that we are talking about should be designed at the initial phases only, so that typically we will be able to take advantage of that pipeline from all these perspectives. This is about the data pipeline or data architecture layers. There are total 8 layers. It all starts with ingestion, collection. Then we talk about pre-processing. Then we talk about storage. Then we have analytical or query. Then finally visualization. These are the 6 standard or typical data pipeline flows. But along with this, we'll also have security layer and monitoring layer. So total, there will be 8 phases or 8 points that we will have to cross-verify. The data ingestion is nothing but the layer where the systems are integrated. Okay, the first thing. Then once this data ingestion is designed, ultimately we are identifying what are the various sources, and then we are trying to integrate. Now, once we have the ingestion layer figured out, then we will collect the data. So we will integrate multiple systems so that the data can flow. And when we say data collection, we are trying to get the data from these different sources which are connected. So ingestion is a step you can imagine there. We are trying to integrate different systems, right? And then data collection is to get the data. Now, once the data is at hand, we will do pre-processing. Pre-processing will ensure that the data is always arranged in a specific format so that right, the data is flowing from one system to another system, and that too in an expected format. The data is basically being pushed to next layers. The most difficult part would be on the storage layer, because a lot of decisions have to be taken, and unfortunately the decision has to be taken from management perspective by considering various aspects that we need to look at. The point is, here we are trying to identify what software should be used to store the data. Finding the right storage solution becomes very difficult, because scalability is something that we will also have to try and consider when we are choosing the storage device. We cannot keep changing the storage device, right? Storage solution. Once we decide on a storage solution, we'll typically stick to it. But when we are doing that, we need to think ahead, plan for scalability issues, and then decide what should be the size or what should be the right solution for your storage software. Eventually, the data becomes large. Okay, so whatever the solution that we're designing now, is it scalable in future? If you say 100 terabyte storage device is required, and if your organization is generating 1 terabyte data per day, then after 100 days, your storage is gone. Right? So we need to typically have identify the right storage device, storage component that we need to use in the system, and multiple stakeholders will get involved in deciding that particular solution for this particular area, this layer, storage layer. We also have query layer. Query layer talks about your analytics. This is where you're going to ask the right questions and try to seek the answers. Those answers that we are getting, we are also trying to visually represent those answers. Now, this is where we will get value to the data. So these are the typical 6 layers, from data integration to or data ingestion to visualization. But after this, we also have 2 additional steps. One is the security. And to implement security, we will use various standards. One of that is ensuring that the username passwords are, that the authentication system follows certain rules and regulations. The access controls will also have to be maintained appropriately. There could be cases where the data is very easily readable. Right? So in such case, the data may get hacked. So we need to ensure that the encryption of the data is also done. Then we keep auditing the access which is done by the users. Right? Data auditing is also something that we keep doing. Yeah. Then we have monitoring tool. The monitoring layer will ensure that the data is continuously moving from the source to destination, and that too without having any issues. Of course, security layer is one of the layers, but we'll also try and see what is the data getting generated at the source and what do we have at the destination. There shouldn't be any loss in the data while the transformations are happening, right? So we keep that in mind in monitoring layer. So these are the typical defined different architectures that we have. All right, so remember when we talk about data flow, we basically are talking about data pipelines. Pipelines are nothing but the sequence of series of steps that we will ensure are implemented so that the data is moving from one flow to another location. The design of all these typical nodes or entities where the data is moving is explained in data architectures, architecture diagrams. There are certain standard architectural designs also. We'll be talking about that now. And when we talk about these data pipelines, we will have batch pipeline, live streaming pipeline, and a CDC pipeline as well. And change data request pipelining is also there. Depending on what we're trying to achieve, we will have to choose one of these three data pipelines. And the typical steps in your data pipeline or data architecture are around. They basically start with integration layer, then ingestion, then we have pre-processing, storage, then we have query, and visualization. 6 steps. And post this, we also have security and monitoring there. So there are total 8 steps that we will have to watch out. If I replace these 2 points positions, then it becomes ELT. Right now, this is ETL. All right, so we have data architectures also. Now, we'll talk about 2 standard architectures that are used by the industry or have been used by the industry. In fact, today also we use this. Typical standards that we have for pipelines. There are 2 different pipelines that we will be speaking about. One of that is called as Lambda. And we also have something called as Kappa architecture. So we basically have these 2 architectures that we will be talking about now. Okay. Before proceeding, we'll take another short break and come back. Too much of theory and all that, right? So post-lunch sessions, we'll have to be a little cognizant. So we'll take a quick break and then come back again. 10 minutes. And post that, we will talk about the data architectures. Lambda and Kappa. All right, please go ahead and come back after the break. So friends, we talked about data architecture steps. We talked about 3 different types of data pipelines that we can formulate. We talked about the differences between data warehouses and data lakes. We also understood when to use data warehouse and when to use data lakes. Typically, we talk about data warehouses coming into the picture when we have ETL pipelines, where we transform the data and bring some consistency with respect to the structure. Then we can use data warehouses. Whereas if you are using ELT pipelines, where we are first dumping the data for the archiving the entire data, raw data, and then when we want to experiment, we can give the schema, transformation. In these cases, we will use data lakes. Now, when we talked about data architectures, we talked about 8 layers or 8 phases that we typically have. And security layer and monitoring layer are part of all the 6 layers that we have, which ensures that the data is reliable and consistent. Now, after all these discussions, we need to actually try and understand how these data flow diagrams are actually, data flow strategies are implemented. We have certain standard architectures which are typically used in almost all the business scenarios. One such architecture is called as Lambda architecture. Very, very popular. When we say Lambda, we typically write like this, right? There's a shape, inverted Y. So explaining this Lambda architecture, we need to see that we have 2 different layers that data is coming from. And then from these 2 layers, we basically take the data for serving purpose, for querying purpose. Lambda architecture is basically the architecture which basically is designed to have the information extracted from large amount of data, big data. And in order to process this, we typically have 2 layers or 2 infrastructures that we try to bring together. One is the batch system, the other one is the streaming system. So Lambda's architecture that basically we talk about will have 2 branches. And the architecture design is like this. It actually contains 3 layers. Of course, this is where your results are coming in. The input sources have 2 branches. Offline branch and online branch. We call it as batch layer and speed layer. Batch layer is where your master database is stored. When we talk about master database, this is the historical data, offline data that we have. The serving layer is where we talk about live data, real-time stream. Sorry, serving layer is, my bad, is the end layer. Business intelligence tools are used for visualization purpose, for example. This is where we get the results. Speed layer is where we have live streaming. So these are the typical 3 layers that we have. Now let us try and understand what does this speed layer and batch layer means, and right. Let's try and understand this image, this image. Using a simple example, let's talk about a scenario where we have a lot of historical data. The best example that we can think of is e-commerce. Let's say Amazon. You are the customer. Your customer details are stored in the database. This is your historical data. All the transactions of the customers which are done till now, let's say till today, right, or till yesterday, are your past records, past data, right? This is nothing but your historical data. This is your master data. Master data record or master database. Now let's say you are one customer customer 1, 2, 3. This is your ID. Okay, your customer ID is 1, 2, 3. All the transactions that you have performed till yesterday are recorded in the database. Okay, this is your past information. We call this as batch layer. The processing about your details are happening in the batch layer, where we try to connect to the database and try to look at all the transactions that this person has done. Now let's say we have a scenario where the customer is logging in now. So this customer 1, 2, 3 has logged in Amazon now. Has logged in to Amazon. So what happens is, using the website analytics, right? Website analytics, we will try to track the user. For example, what product page the user is logged into, what product the user is watching, which page the user has opened, how much time is the user spending on that particular page, what all different pages the user is opening. Are these similar products, different products? If they are similar, what are the categories? Among these, which page has the customer been for the long time? Within that page, what section the user is spending more time? Right? And this is all the live data that we are tracking, or the Amazon is tracking with respect to this particular customer. Now, using the past information, right? Using the past information and using this information, we will be able to get a lot of details about the customer. So we will do the query and get the results. For example, how many times the user logs in before a product is being purchased by that particular customer? When did the customer purchase? Did the customer purchase only when there are offers? What kind of amount would the user invest in purchasing the products? Will the user purchase only when there is an offer? That's a very important question that we need to look at. If yes, then to ensure that the user makes the purchase in this particular session when the user has logged in, we give a customized or personalized discount coupon. Yeah, so this is a typical use case where we use information from batch layer and live data, live streaming layer. This is the result. This is where the query happens, and we will have the typical serving. Serving is nothing but where you're going to give me the results. Right? So if I have to draw the diagram, I'm saying this is your batch layer. This is speed layer. And this is where you have serving layer. So information comes in both the layers, and then you get the outcome, whether the user purchases or not purchases. So because of this shape, right, it's called as lambda architecture. This is one of the standard implementation with respect to the data flow designs or data architectures that we speak about. There's a question. What is metadata? Now, how many of you can tell me what is metadata? What is the meaning of metadata? Who can tell me? Nobody. Data of data? No. Data about data, okay. Population data, no. First information, no. Details of the data, okay. Okay, from a textbook perspective, metadata is nothing but data about data. Okay, this is how textbook definition can be explained. But what does this data about data means is, I have a database. Okay, this is one of the table that I have. Now, what does this column means? Definition. Right? This is called as metadata. The definition about your data is called as metadata. So data about data is nothing but information about that particular data that we are using. Okay, so that's called as metadata. In other words, we also call it as schema. It's just a name change, metadata. For example, if you're reading a book, you'll have index. Index is metadata. Index talks about the information about the book, the content that is there inside the book. So index is the data about the data that we have in the book. Okay, so that is a typical definition of metadata. We talked about Lambda architecture. Now we'll talk about Kappa architecture, friends. Kappa architecture is an alternate option that we have. It's not a replacement. Please don't think that this is a competition for Lambda architecture. Not exactly. This is another typical architecture design that we have, which is kind of popular. So Lambda architecture is one such example. Kappa is also one of the examples that we can try and apply. In Kappa architecture, we will have a single layer. We don't have multiple layers like what we see in Lambda architecture. And in Kappa architecture, both real-time and batch processing are done in a single layer itself. We don't have a separate layer for batch and separate layer for real-time data processing. So this is the typical steps. The live streaming incoming series of data, right? So live data that is getting generated will first get into a system, which basically will allow us to ingest that data, right? Messaging engine like Apache Kafka, which is used for stream the data. So your live data will come into these systems. And from there, we will read the data and do the required manipulation. And once the data is transformed, we will apply the data into OLAP, where we can perform our queries. So it's kind of using a batch mode processing on live data. So both live and batch mode are typically combined in single design. So this is one of the alternate options that we have, but it is not a replacement. And it also supports near real-time analytics. Okay. So if you see incoming data, here we are using tools to ingest the data and then store that into a OLTP system for performing, OLAP system for performing analytical solutions. And when queries are coming in, the queries are being done on this particular data store itself. So as soon as the data comes in, it gets transformed and stored into the analytical system. So we only have one layer. We don't have multiple layers. All the data becomes batch layered data for your end user, but everything will be real-time live data for data generation perspective. So live data is also getting converted into offline data. Kappa is represented like this. It's like N, lambda and kappa. The advantages basically is that your lambda architecture will use the historical data for with effective usage. It has an effective usage, right? And because of the complete historical data that we are using batch mode, right? So the chance of errors is less is what we see. And it also tries to balance the performance by doing the right speed with reliability balancing. Fault tolerant and scalable architectures have to be used, and right, they will be used for data processing. Whereas the advantages with Kappa architecture, you can see that live data, whatever the data that we're getting, is treated as live data. So there's nothing like batch layer, separate layer is not there. And we are only trying to retrain when there is specific requirements. So once you design a machine learning model, we can keep continuously using it because we are only talking about live data processing. Right, and because we are using only live data streaming, we can design our infrastructure upfront. With respect to scalability, we will not really have much issues here. Okay, horizontally scalable systems. There's something called as horizontally scalable systems. Distributed systems can be used here in short. That's what it means. Vertical scalability is something that we don't want to have. For example, if I have a small server, i5, 4 GB and 500 GB storage. If this is my server, if I have to upgrade it, we typically go to a server which is having a little higher capabilities, i7, 8 GB, 1 TB. If I want to upgrade it, probably I'll go for i9, right, 16 GB, and maybe 1 TB or 2 TB or whatever that is. Right? So typically we are trying to upgrade the servers. That is called as vertical scale. Horizontally scaled systems means if I have one system and if it is not sufficient, then I will add one more system to the right, this first system in over network, and I'll try to take the capability of both these machines. If this is not sufficient, then I'll connect another one. Right? So I'm not replacing the existing servers, I'm adding power or capacity to the existing servers. Right? So this is the horizontally scalable systems means. We typically call this as distributed framework, which are the go-to option for dealing with big data systems. Hadoop, cloud platforms, and all those things, they use this distributed framework capacity for dealing with large amount of data. Right? And less resources are used because we have a single technology stack, whereas here we have two technology stacks. One is offline and the other one is online. Two different systems are required. Here we will have only online, right? So lesser resources are required. These are the advantages. Now, if I talk about disadvantages, Lambda and Kappa kind of complement each other. So the disadvantages in Lambda is that we need to have code overhead. We want to do a comprehensive processing because we need to take the advantage of all the historical data along with the live data. So definitely the coding that we talk about is a lot. And when we try to retrain the model, you'll have to do retraining of the entire historical data. Right? So the batch cycle that we talk about is going to be very expensive because it has to retrain on the entire huge amount of historical data. Now, once these systems are designed, migrating will become difficult. You don't want to typically make any changes to the Lambda architecture design once it is made. Now, if you see here, I have two layers. That means I'll have two systems, two set of infrastructure systems, two code repositories. Right? So everything becomes double, in short. So errors could also be double. Right? So that is another problem that we have. And a lot of duplicate modules will be there in both these systems. And that's another drawback. Now, in Kappa architecture, because we don't have batch layers, when we are doing data processing on the live data that we are getting, there may be a lot of errors that might be creeping in. Because we are not verifying this live data with batch data, we tend to miss a lot of these errors. Right? So that is one disadvantage that we have. In short, errors validation is something that we cannot do. We can do, but it is not effective as we have in the Lambda architecture, because we have two systems here. The comparison of the errors, the validation of the errors can be done much effectively. Yeah, the Kappa architecture is practically not easy to implement. Okay, that is another challenge. Lambda architecture is very easy to implement because two distinct systems are there. Majority of the information or majority of the training happens on the batch layer. Whereas in Kappa architecture, it is not that easy. Okay, and yeah, deeply is kind of validation, data versioning that we're trying to see. Because everything is live data, we cannot do the data validation and all that. It becomes too difficult to implement that particular part. So implementation wise, Kappa architecture is a little tricky and difficult one. So these are the pros and cons of Lambda and Kappa architecture. So this is right. This is the advantage, sorry, disadvantage and advantages. Okay, so this is, once again, this is the diagram for Lambda architecture, where we have two layers. From the data that we get from both the layers, we are trying to do the queries to get the results printed on the serving layer. In Kappa architecture, we have a single layer, live streaming data, which gets converted into a batch layer. Right? And the queries are done on this particular single tech stack to get the results. So these are the advantages and disadvantages. So we talked about various data pipelining steps and architectures, standard architectures that we see in the industry implementation part. Now coming back to the deployment part. So CRISP MLQ methodology speaks about implementing the ML ops standards right from go. Prior to this, we had CRISP DM methodology. If you have any old students, probably before COVID, right? If you have learned your data science concepts, then before COVID, even we used to follow CRISP DM methodology. Entire industry used to follow CRISP DM methodology. Data mining, DM stands for data mining. Our focus here was only to develop a machine learning solution on sample data. So we call this as POC. Okay, but this POC has to be productionized. If I have to implement this on production level, then it's not going to happen. There were a lot of practical problems arise, the challenges arise, and to overcome all those challenges. There were new solutions that were developed, and adapting to those new solutions, new steps. The CRISP DM also evolved and became CRISP MLQ. Right? Everything will evolve, right? So it upgrades. So we have CRISP MLQ methodology. So when we talk about machine learning models development life cycle, as we discussed, CRISP MLQ is being implemented. We typically use this methodology. Our focus as part of the development would be on the training part. Designing your model, training your model on the historical data. So we train, if you look at this, we try to train the model. We will make adjustments to get the better results on your data. So when new data comes in, we train, we tune, again we will verify. So this is the training part which is being focused here. But when we talk about inferences means drawing the results from the training that we have done. Here we basically try to serve the best solution. Whatever the solution that we develop, right? We serve it. That's how it means deployment. Serving means nothing but deployment. Deploying the solution. Now, once we deploy the solution, the system will be, the stakeholders, the end users start using that solution that is deployed. This gives us an option to monitor the results. Once it is deployed, only then you can keep a close watch and understand what is happening, right? So we are monitoring here to understand whether the solution is working as expected or not. And if it is not working as expected, and whenever there are certain changes required or updates required, we do that. So it's a typical 8, right? This is like more like a 8-step, like this. So this is the typical flow, 8 flow. Training and inferencing. And this is a continuous activity, friends. This does not stop. Okay, this is a continuous activity. Because your business does not stop, business will keep generating the data. Right? Now, if you look at this diagram, a very, very famous diagram, which emphasizes on how important is it to understand the deployment related strategies. When we talk about deployment related strategies, we are talking about how do you operationalize, how do you ensure the solution that you're developing from machine learning perspective is being used in the production environment, operationalizing it, right? So there are certain validation steps that we need to look at. This diagram, which is an illustration that is given by Google way back in 2015, shows that the focus that we are giving on ML code development is so small compared to various other things that we will have to look at when you are trying to productionize your software. But unfortunately, as a data scientist, for developing a POC, we will always emphasize on the ML code part. Now, this is one very, I should say, disheartening thing that I observe from my students who work on projects. I try to educate them, but there are some of the students who are very adamant and they don't want to understand. Right? I'm using all these words because I experience this and I feel so sad and disheartening. Whenever we talk about a project, machine learning solution that we want to develop, right? A data science typical project, I mean. when I give the problem statement, okay, generally the flow is like this. I describe the problem statement. I will talk about the expectations. We will define the domain where the customer is working. What is the problems area that the customer wants us to focus on? Now, once this description is done, immediately the next question that I get from my students is, will you give the data? Can I get the data? So this is the first thing that they will ask. Is this an assignment? No, this is not an assignment where I want you to develop a machine learning model. No, I don't want you to do this. I can get this done. Code is readily available. Don't you think I can do clustering on this data? Don't you think I can do knife based on this data? Don't you think I can implement neural network on this data? I can do that. Right? It is not about building a machine learning model on the data which is given to you. No. Data is, of course, the integral part and main component for developing machine learning model. But your approach should not be data first. Change that attitude. Analytic solution is to analyze things and then provide a solution, not take data, build a machine learning model. So your approach should be do market research, understand what is this domain all about, what kind of various competitors are working in that area, what is this problem area that customer is speaking about, how is it negatively impacting the business, who are all the stakeholders who are getting impacted, are there any research papers or any articles, any material or content which is available which explaining this particular problem area in detail. Are there any solutions already provided which solve this problem area? When I say market research, unfortunately, we also say Google. You have to Google for these things. And this is also something our students, my students, don't take it positively. I mean, when I say, hey, you have to study, try and research things, they come back and complain saying that Sharath is not explaining things. Sharath is asking us to Google. Of course, I'm asking you to Google. Why? So that you understand everything. If I tell you what is the learning that you have, better I do the project. I don't have to use your capabilities. Right? So you need to understand that ML development is the minimum part, right? That is not a big thing. You have code. By the end of the course, you understand what algorithm can be used on that particular data to solve a specific problem, to predict a specific value. Okay. Logically, try and design your solution, which includes all these areas. That is the true implementation of data science skills. You talk to your technical team, subject matter experts. Talk to your entire, what do you call the stakeholders, customer stakeholders. Ask relevant questions. When you understand the problem area properly, you will be able to define all these aspects that you have to cover so that the solution that you're developing here can be operationalized. Right? Because if you ask me data, I'll give you data. Fine. I have 5,000 observations. I'll give you. What you'll do, you'll simply say, hey, we have applied machine learning model. I applied regression, simple linear regression or linear regression. And I found error, which is XYZ amount. And then we deploy. I don't want this kind of a solution. This is nonsense. Because do you think the business is only sitting idle after generating 5,000 records? No, right? Continuously, the business moves on. That means more and more data keeps generating. The model that you're working on is only being developed for 5,000 records, then I don't need that solution. What I need is an entire architectural design which says that, hey, this is where your data lies in your business. That is your source. Then we will collect the data using XYZ Python library and get that particular data into Python for pre-processing. Now, the pre-processing will automate the things. We have designed the code in such a way that it does all the pre-processing things. The pipelining is done in such a way that all the conditions are verified and an appropriate solution is developed here. For example, on the 5,000 sample data that was given, we found that dummy variables were required. I'm going back to the first discussion that we started today, right? As part of our session, I explained about this. We will do scaling. We also observed missing data, NAs. So we will be doing imputation. But if I find outliers in my data, if new data contains outliers, then I'll also do outlier treatment. Maybe Winsorization is what I'm going to define. So we will have to write the logic in such a way that the pipeline in such a way that it verifies for outliers. If found, then Winsorization will be implemented. So everything has to be validated. Once the data is collected, we validate it and then perform the appropriate step. Right? And then we will partition the data. So here we will have train and validation. In the projects, we have to do this. And on the training data set, what characteristics we will have? Again, stats have to be captured. Validation data, stats have to be captured. We are verifying for bias in the data or noise in the data. Right? And then we will try and use an appropriate machine learning model here. Depending on what is our end result, we will choose the machine learning model that has to be typically trained. So we will have train validation. So we'll also get the hyperparameter optimization implemented. Okay, hyperparameter optimization is done. So we'll have training, validation. Once the solution is obtained, as per the benchmarks that we decided with respect to the first step of CRISP MLQ methodology, where we talk about the success criteria is also being defined. Using those benchmarks, we will decide whether the model that we have designed here is an appropriate solution or not. Right? And once this is done, we will validate or evaluate the solution on the test data as well. Now, always remember the pipeline for any data that we are using here should be decided like this. Right? It has to be defined in such a way that it goes through all these validations. So test data also has to be passed through this pipeline. And then we will get the results which can allow us to generalize this. All right, so that is about your flow. And once this is validated on the test data, if the results are accepted, if it is acceptable, then we retrain it on the 100% data set. That model will be saved for integration purpose. Okay, so the focus is always on, typically on building the machine learning model. But when you try to deploy it or when you try to implement that model for the real data, new data, the model will struggle. It will not perform as it is performed on the sample data. This is because we are not verifying all these points which are illustrated in the paper here. The another important point is continuous learning, because we are talking about machine learning. So these are the aspects that we don't actually focus on. The infrastructure that has to be used, the logic which says that when new data is coming in, we're doing prediction, but as the new data comes in, that means more and more data is also getting accumulated for us, right? So training data is increasing. Now this new training data also should be used for training purpose. So is your pipeline designed in such a way? If yes, fine. If not, then we are losing out on the new changes that are coming in the business. Every business changes. That means your data will change, and because of the data, the expectations, the performance of the model that we have defined is also changing. We'll have to track all this, right? Maintenance and monitoring is all about this. We do not emphasize on this, and that is where we are losing the project. So we are not able to implement it in the right way. Right? So configuration. We're talking about software, hardware configurations, infrastructures, right? So the configurations. Data collection strategies have to be used in such a way that we do not have bias or errors entering into the data. And when we are doing the data collection, we'll also have to ensure that the relevant features are extracted, not everything. And when this data is getting collected, the features are getting collected, we are also trying to ensure that the data is being verified with respect to all the errors, the noise, errors or noise means same, bias that we might have, right? So all those things have to be verified. The versioning will also allow us to compare the different variations in the data that we are getting. Machine resource management. The analysis tools that we are using. The CRISP MLQ, right? When you're trying to implement this from a project management perspective, project managers will have certain tools like Jira and all those tools. Right? So the project managers have to typically be using those to ensure that the flow is followed and tracked. And the biggest area is the infrastructure that you are going to choose, because ultimately it will add to the cost. And of course, performance. And when we talk about the productionizing, we'll always talk about scaling up. But there is another very important point, which is scaling down. It's not just scaling up, we'll also have to focus on scaling down. Okay, so we need to look at both these cases, scaling up and scaling down. All right. This is the again the flow that we generally use with respect to our machine learning development lifecycle. Without MLOps principles is what we have been implementing or developing our machine learning solutions. We don't follow these strategies. This is the diagram which basically is followed. We will have data source, let's say a database system. This is where your raw data lies. We are trying to process that raw data and capture the relevant data itself. And then we also do EDA, which gives us the reports. Data analysis is performed here. And then comes the fourth step, which involves your machine learning model development. So we do the processing of the data, partitioning of the data. Then we will use train and test model, where we will try to build the model on the training data, tune it, validate it, and then we also try to tune the model, and ultimately we will have the test data, which gives us the generalized error or generalized accuracy or performance levels that we can have for the model. Now let's say we basically have benchmarked here, and we reached that benchmark with respect to the model. And we are satisfied. The best model is captured. So this trained model, which is typically considered as the best model here, will be pushed into the code repository. Now, this code repository is nothing but a location where we are dumping all the latest of the codes that we are developing. Code management, you can say. This is tools. There are tools that is GitHub. We will be talking about GitHub. GitHub is one such tool which allows us to manage the code that is getting developed. So we store the code into this repository, that location. That's all. From a data scientist perspective or machine learning implementation perspective, this is what we typically do. Okay. Now, once this code, the best code, is updated in the code repository, we will get our operational team or software engineers to take that code and then integrate into the existing system of your customers' deployment. Now, once the deployment is done, the model will be started or is used by the end users. Right? Each model will have some functionalities, and users are trying to utilize the functionality of the model that is getting deployed. So model starts serving, and users are starting to exploit the functionality. Right? The deployed model offers its services and gives some functionality. So end users will start using it. Our teams should collect all the data which is related to the model usage. So it will include the performance, the results, the input data that the users are passing, the size, the speed at which the processing happens. So all these typical information that is required is collected. Right? We capture all the data and then we segregate it and push the data and store it into the data store. Right? So we capture all the data and forward it to the repository, data repository or database software. Now, once it is there, our team will come back, data scientist team will come back and try to analyze the performance differences. Right? It will evaluate the model's performance and if there are any changes and all that, right? So we try to capture all that information from this data that is getting stored into the databases. And if you see anything which is required changed, we'll again follow this process. Right? This is the cyclic process that we see, where we have data scientist team and operations team working in to ensure that the solution is deployed. But this is without ML ops standards. So we will have a challenge where we are having too many resources, too much of redo work, right? And a lot of things ultimately are added as an overhead in this particular solution. With respect to the productionizing of a machine learning solution, it's very easy to build a POC. Once you are familiar with machine learning algorithms and the respected libraries in Python, then it becomes very easy to develop your machine learning model. Right? We will try to focus on these things. And we will try and use Python and develop the model on our local machines. And this is what we do. But what about various aspects when it gets into the production environment after model development? Don't you want to monitor and see if it is working appropriately, correct or not? Don't you want to see whether the input data and the data that we used for developing the model is having similar characteristics or not? Right? So a lot of things come into the picture. To make you understand here, you can see the rocket image is there. And we are saying that launching is easy. You just press a button, which will ignite the fuel and the rocket flies. But operating it after its launch is something that becomes very difficult. So if you see rocket is launching, the purpose of the rocket is to fly in a specific orbit or path, get its work done, and then fall back, come back. But when it is coming back, it cannot just randomly come back. It has to be following a specific flow, again, a specific path while it returns, so that there is minimum damage. So keeping the rocket in that orbit, ensuring that the rocket is completing its job, right? And then returning back. That means your satellite probably is one of the satellites that you have. You're pushing that into the orbit of space. And then the rocket has to come back. It has to deliver the package and come back, right? So that is the solution. That is the expectation. And right, rocket should just not fall like this, right? It has to follow a specific orbit. So controlling that entire flow becomes a really, really difficult job. Why? Because we will have to continuously monitor it. The training is fine. We have developed the training, a model on the training data, and we are expecting some results. So we capture those performance metrics on sample data. But when you serve it, there will be new data that comes into the picture. Once the new data is used, the results that we get also have to be recorded. The metrics have to be recorded, and we need to capture the variations, the difference in the metrics. So we'll have trained data and serving data. There will be a gap. We need to capture that gap. Right? So gap in the model performance during the training period and after the model is deployed. There shouldn't be too much of gap, but we don't capture this. We need to capture that also. Because the performance of the model may drop over time. We need to identify that. The model might drift. Why is the model drifting? Because the data that is coming in, the new data that is coming in, will have some changes. Why is data changing? Because the objectives of your business might change because of the business evolving process. Any business that we talk about will evolve, will improve, right? Will change. So we're trying to see the effect of the business change in the data. And in order to capture that, we need to capture the metrics of various data that we are getting. And when you compare, that will tell you the data drift. And if there is a data drift, then model also is to be drifting. We are also capturing the metrics for the model to identify that drift. The data freshness is also something that we'll have to look at. As an example, what does data freshness mean? The model that we have developed, the trained model that we have developed, could be designed on a data which is on a one-day interval. As an example, I'm saying. So the granularity is day-wise. Okay, we have day-wise granularity here. Daily data, as you know. But when you are trying to deploy the solution, it has to work on a granularity on hourly data. Do you think a model which understood a daily data will work on hourly data? Maybe not, right? So there will be a lot of difference, obviously. Right? So that is something that we'll also have to keep in mind. Now, whenever new data is coming in, as the business evolves, we're saying data is continuously flowing in. So to capture the new changes that we're getting, right, with respect to the business evolving process, we might want to bring in those changes into the model. So we will have to retrain, but how often we train the model on the complete historical data. Say, for example, I'll have historical data of 5,000 records. After 1 month, this data could have become 8,000 records. New data is coming in, right? 3,000 records have come. Do you want to still continue the model which is designed on 5,000 records? No, right? This becomes historical data now. So why not use total 8,000 records and retrain the model? If I have to do that, then my question is, should I do it after 1 month where I have 8,000 records, or should I do it on quarterly basis? That is another question that we'll have to answer. How often the model has to retrain itself? And how much of the old data that we have to use? So all these are related questions that we will have to also answer. Okay, and in order to implement the ML Ops solution, there are readily available products which allow us to design, develop, train, maintain your ML solutions from end to end. You don't have to do anything. Everything is automated end to end, including deployment. Okay, there are certain products. These are a few of the examples: Data Robot, AWS Cloud SageMaker Studio, Converge.io is another typical solution. We have Azure Solutions, Machine Learning Studio. We have Vertex AI, which is GCP solution. There are few solutions that we are talking about. Okay, so we may have a number of different solutions that we will have to use. But these solutions that we are typically looking at are the readily available products which allow us to implement an end-to-end machine learning solution. Right? These are products, examples, readily available solutions. The advantage is that these solutions will be able to very easy to use. It's like navigation, drag, drop, or click next, and right, get your things done. So very easy to use. You don't need to learn anything. Everything is in English. You just read it. Description will be there. You read that description and then job done. You use that particular option. But the disadvantage is that these are costly. Readily available solutions will always be costly. Right? It's easy to use because you have very refined and very simple GUI, and everything will be drag and drop. You'll have a single centralized controlling system which can be used to manage and serve your models. A single solution, right? So we'll be able to have a single platform to do everything end to end. We'll also be able to have documentation to understand what is happening in these various experiments that we do, testing that we're doing, right? So all this documentation will allow us to look into the advantages. Now, when we talk about disadvantages, expense, yes, it is costly, and you'll not be able to do a lot of customizations. That is another drawback. You'll be using whatever is provided, the solution. But if you want to do any customization, it becomes very difficult. And you need additional resources like human resources, the infrastructure resources, all is adding to the cost. That is where we try to look at alternate options, open source alternatives to avoid this cost. And these are some of the advantages and disadvantages with respect to open source options. All these things that you are looking at in this particular slide are open source solutions which allow us to do the deployment, end-to-end deployment of your machine learning model. But this is more manual. These are open sources, so they don't cost. And there are too many options that we can actually take advantage of. A lot of options are there. And anything that you're developing will be in-house. You'll be able to own it. It becomes intellectual property of the organization. And we can do a lot of customizations, develop a lot of things. When it comes to the disadvantages, we'll have a lot of time required to develop the solution because learning curve will definitely take time. You don't know, right, which works, which solution works, which solution will not work. So it takes typically a lot of time. Learning curve is large. So identifying the right tool is also one of the points that we'll have to look into. That will also kind of take a lot of time because so many options are there. Choosing the right option will be one of the tasks that you have to do. And because of these customizations and open source things, and because MLOps itself is a new area, we do not have skilled professionals who can actually handle all these particular tools and techniques, open source tools and techniques. This is the drawback that we have. Okay. Now, if I talk about implementing the machine learning model using the MLOps standards, right? You can see the flow is very similar to what we have seen previously, but there are certain steps which are becoming an integral part of the entire deployment stage. So we have feature store. This is your raw data store. Okay. Typically your data source. We do analysis. And then, we do automated model development and analysis. So automated EDA will be done, model selection will happen, data partitioning happens, hyperparameter tuning optimization also is done internally. Everything is automated. We call it as auto ML libraries being implemented. Right? And then we get the modularized code. The pipelines, the sequence of steps that are implemented here are part of your code. Right? The entire pipeline is built in such a way that we take the data from the feature store, do the feature engineering, select the appropriate features. So the sequence of steps that we have are added into the code. Right? And every point that is there in your code, source code, will be tested as well. And that becomes your modularized code. This modularized code is dumped into your GitHub repository, for example, code repository. And from the source repository, it is going to be implemented or deployed. So here we are again doing the testing before it gets into the deployment stage. And the solutions that the pipelines which are actually passed, those are only selected. The pipelines which are failed in the testing are not included. Right? So we take the source code in which multiple solutions will be there as part of your code development. Out of that, we are taking only those things which work. We package them together and use that for deployment. Now, once the solution is deployed, we are again doing the training here. Right? So again, we take some data from here. Right? And then we'll try to do this particular training. But yeah, so model deployed the data. After deployment, we again do the testing on the training data set. So we take the training data set from here. We'll have train data, test data, right? So we'll use that data for testing the deployed solution. And then we will register the solution, the model that we have tested. There will be many models. The tested model will be registered for usage. And then the registered model will be started to be used, serves the functionality, the features. And then again, the flow remains same. We capture the metrics, the user's data and the performance of the model, everything is getting stored, right? And we have here. And this will also allow us to do retesting if it is not working as appropriate, right, or as expected. So here we will have triggers which will allow us to retrain or recheck the deployed model. Testing and right, only tested model will be registered and all that. So this is like a cyclic process. The deployed solution also has to be validated every now and then. So there are certain changes that you have seen here with respect to the previous implementation. So here we are doing the training, here we are doing the deployment. Right, so this is a typical flow of your machine learning development life cycle. Right, now next, let us talk about the comparison of data science with MLOps teams. Data scientists with MLOps teams. Data scientists we have already discussed. Right, we are basically people who have statistical machine learning capabilities. We are trying to analyze the data to identify the problems and the solutions as well. Right, and these are the typical things that we have discussed. Coming to the machine learning engineers, MLOps engineers, we need to have basic idea of machine learning algorithms. We don't need to be an expert in machine learning models. You don't have to be typically a data scientist. But understanding the machine learning algorithms is important because ultimately we will be deploying it, plugging it into the system, production system. We also have to ask these questions because when you are trying to design or deploy or integrate your solution, we will have to design it in such a way that we ensure that these three things are implemented: continuous integration, continuous development, and continuous training. Development is nothing but continuous training in this particular case. So if you have to retrain, how often you have to retrain and deploy? And that is another thing that we need to also identify. For different scenarios, the interval will be different. We cannot have a standard fixed answer for that. So it is a subjective call that we will have to take depending on what solution you are developing. But you need to understand that so that you also implement that particular point in the deployed solution. How many different predictions we'll have to do, how many times you'll have to do, right? And can we automate it? If we can, then what are the various steps of your machine learning workflow that we have to automate? Right? So should I automate everything end to end? Maybe in certain cases it doesn't work because data pre-processing would be very, very dynamic for different cases. Right? So you need to also ask these questions. Implement the model, right, within an app, integrate it with respect to, let's say, an application which is already there. Is it required? Yes. If yes, then we need to be able to do that integration. This is a typical development skill that we have. We also have to ensure that the pipelines which are designed by your data engineers are optimized for performance perspective. Right? So what kind of queries you have to write in order to get the relevant data? Because if you're bulk loading the entire data and then doing pre-processing, then the load on the database increases. Do we require that? Can I optimize that particular code in such a way that at the database level, we only write the queries which capture the relevant data itself, rather than taking everything and then doing pre-processing? Right? So these kind of things we will have to do. And this is again, typically a development skill. But you need to be a core developer if you have to optimize that entire solution. So you also need to have SQL and NoSQL skills here, database skills. And you also have to have the skill which allows us to maintain the code repository, especially Git and GitHub, right? These are very, very popular tools that are used for code versioning or code management. So these are some of the capabilities that your ML engineers should have. Right. So this is bringing us end to the theory part. I will talk about Git and GitHub now, but we will take a quick small break and come back. And post that, I will be talking about the GitHub repositories. All right, so yeah, we'll come back and discuss about this GitHub repository things. Okay, let's take the break. All right, friends. So we discussed about the various strategies that have to be considered when you're deploying a machine learning model. And in order to do this, these steps, the strategies that we'll have to consider, right? In order to do that, we can typically use the tools which are available in the market. These are readily available solutions. Generally, these are cloud-based solutions, cloud-based platforms, which are providing us readily available tools. The advantage is that they are very easy to use, and they have centralized controlling units, they have documentations, the easy GUI, right? Those are the benefits. But the disadvantage is the cost. The other type of tools that we have is open source tools. Now, before I talk about open source tools, one thing you need to understand is the open source tools list that we have seen. Typically, all of them are developed by Google. All of them have Google's hand in them. Right? So Google is one organization which is very actively investing their time in developing these open source platforms or open source tools, free tools, which can be used for doing an end-to-end deployment of a machine learning model so that it can be productionized. Typically, we will have to use MLOps standards when you are doing the deployment. And one of the critical steps that we will have to ensure we learn and practice is the code repositories, right? Handling the code repositories. And here, today we will be talking about Git and GitHub tools. What is Git and what is GitHub? There are two different things. So to start with, we are trying to compare these tools, and then we will try to utilize one of the tools which basically allows us to do the code management. Git is an open source software. It's a software, okay? Open source distributed version control system. It's typically a software that you'll be able to install in your system. Whereas GitHub is a service. It's not a software, it is a service that you get. Because it is a software, you will be able to install it in your local computer. Right? And it is a service. So you will have an interface that you can use. You can also have a command line interface. You'll also have GUI interface. Right? And for Git, because it's a standalone software, internet is not required. You can work on your local machine. But it's a typical service which is hosted, which is provided to you. And you want to utilize this, then you will have to have internet connectivity. The Git is specifically used for doing version controlling of your code. So any code changes or details that we basically have will be tracked. And there will be multiple people who might want to collaborate and do the development. We'll also be able to allow those kind of coding collaborators, right, to work together. So coding collaboration is enabled or something that we can achieve using Git. GitHub, on the other hand, is a service which does the same job. And it also has a centralized repository that can be used for parallel code management and the code development. The GUI option for Git is a local desktop interface. Here also we have GitHub desktop, which is basically a desktop interface, which can be used to access the services of your GitHub, which is hosted service, right? Cloud-based service. So you can use a web-based the interface, or you can also use a standalone application, GUI application that can be installed on your local desktop. Whereas here you'll have a very, very basic GUI. There are third-party GUI interfaces also for Git. GUI means graphical user interface, a small interface which gives you a very easy access to the services that these softwares provide. So a very small GUI-based application is there for Git. It does not have user management features. Git doesn't talk about user management features. It basically only looks at the code repository or code versioning scenarios. And Git is maintained by Linux organization, whereas GitHub is maintained by Microsoft. And GitHub has built-in user management feature also. Right? User controls and all those things can be given. You can restrict the users only to see the code. They do not allow. We do not allow certain users to develop some part of the code. Right? All those restrictions can be done using built-in user management feature. This is a typical comparison between Git and GitHub. You can say using Git, we can try and achieve the GitHub related things. Right? I mean, typically there is a software which allows us to do version controlling and all that, and we use these capabilities as a service. So GitHub is nothing but a service which ultimately uses the Git capabilities. That's how we can probably see it. Now, how do we push the code? How do we manage code repository here? To explain it to you, I'll be using a very simple software here. We are trying to add a machine learning project onto the GitHub. In order to do that, you might want to first have a Git software, install Git in your local machine. I already have installed it. And then I will have to have an account in GitHub. I already have an account in the GitHub. I also have logged in. In the break, I have logged in. This is basically my GitHub account. Okay, once I log in, this is how it shows. Okay, github.com, official account I'm using 360DigiTMG. We'll have to create a repository on the GitHub to start with. Okay, so creating a new repository can be done like this. I will go here and I will say recent repositories, new. I'll create a repository here. I will say ML sample project. I will write the date 09/11, September 11th. That's all. Okay, typical, very simple GitHub repository is what I'm creating. Okay, create the repository on her GitHub. I'll do this. I'll say create. I get this. When I create a GitHub repository, this is some information that I'll also see. Quick setup, or create a new repository on the command line, push an existing repository from the command line. So this is what we are going to use here. I already have a local repository. I'm trying to use that local repository and push that into GitHub repository. So let me open this and let me go to my where is my repositories? Okay, this is my repositories. I think sample project 0911. Yeah, this is just created. So I'll do one thing. I'll remove this. I don't need this. Let me go to the settings and let me delete this. Yeah, delete this repository. Don't need this. I'll just try to. Yeah. Yeah. All right. So I've deleted that. I have only one repository. Let me use this. Okay. That's also a sample repository. So I just removed it. There are certain conditions that are given here, right? These commands is what we are going to use to push a repository from my local machine onto this GitHub repository. Okay. So the steps are, once the installation is happening, we use Git to navigate to the ML project. Okay, so ML project, I have saved a sample ML project here in my, let's see if I have something here. I don't have here, is it? Okay. Let's see, users, data science. I kept it somewhere, I forgot. I'll use one of the existing ones. Fine, let me navigate from here. Okay, so once the Git is installed, I will have to use Git bash. Okay. So let us use Git bash. This is a UI which is given when you install Git software. Now we need to navigate to the project where we have the folder created, right? So I remember this is there in the C drive itself. I should go to that. Yeah, no, not this one. Yeah, I think this is the solution. It should be there in the project. Yeah, that's that, right? So Deva's agenda and all that you can see. So I will be going to that particular location and I will define certain things. So CD, C colon, PWD, C drive, users, buses, data science, LS, these are all the various folders. I'll say codes, LS, I have device, LS, I think this is the folder. Yeah, simple linear regression, right? Yeah, this is the code. So what I'll do is I'll come back to this particular location. And this is where my project is given, right? So this is my project as you. Now, the first step that we do is initialize this particular folder as a Git repository, local repository. So I'm saying, hey, this is my code repository. To do that, I use git init. So it's initialized empty Git repository in this particular folder. This is the message, typical message that you are seeing. Now, once this is done, we are trying to add the project files into something called as staging area. So first you have a repository, then we will have staging area. All the committed files and folders that we have in the repository will be there first put in the staging area. So we are adding a staging area here. Adding embedded Git repository, this folder into the staging area. Okay. And once this is done, the files that we are having in the staging area have to be committed. And when you're doing the commit, we will have to add some message so that you understand when we are doing this commit the next time. So all these are version controls. So when I say commit, it is version 1. So I'll say ML project version 1. I'll do this. So there are 4 files changed and 5 insertions. So these are the things that we have repository, right? So this is the files that we are trying to see. Right? And once this is done, we will use the commands that are there here in the GitHub repository. So these are the commands. You can say copy the link from or push an existing repository from the command line, right? So here if you see, push an existing repository from the command line. So we are using this particular steps. Copy and paste it here. Done. And then right, all the 3 branches you can push your origin master and then right branch, all those things. So I'll just copy paste this branch. I'm calling it as main. You can give any name. This is my main branch. And then I'll say push the entire code into this particular main. So all those things that are there in local have been now moved into this particular repository. See, you have all these files. So empty repository was created. We have pushed everything into the local, into the Git repository. So you can share this repository to your friends or your team members who are also contributing to developing different features, maybe branches of your project. They will not touch your particular code. They will probably develop a separate sub branch and then add it to your main branch. If the team is working on, let's say 2 or 3 people are working on the same code, same features, then every time they make any changes, they have to push, right? So they will have to commit the changes to stage area. They have to add to stage areas, the first thing. Then they have to commit the changes, and then they have to push the code. This way, the centralized repository always gets updated. And when you are trying to develop, you always get, right? You're pushing here, you'll also get the code and then make the changes and then again push it. That way, you're always going to work on the latest of the code that your team is also developing. So as a group, you are going to develop your code. There are a bunch of codes with respect to your GitHub repositories. These are right, some of the things that we have. So this is the last command that I have done. And GitHub commit branch clone. What are these things? Right, the description is given. Then we also have how do we install the softwares and various operating systems. All this is also available on your GitHub repository itself. I mean the URL itself. You can go there and see all these commands. Configuring your local repositories can be done like this. You're initializing your Git repositories. You will also be able to clone your repositories. The branching, how you do branching, how do you merge different branches, how do you fetch your branches, how do you pull and push your GitHub repositories, right? All these are different codes that are available. you have to start using the GitHub repositories for your projects. All right. So this is with respect to your data engineering. Right. We also talk about MLOps. We are talking about pipelining. Right. We are talking about various other features that we need to have in our projects. Like data warehousing is something that I talked about. Data warehouse. We talked about data lakes. Right. Data architectures, data pipelines. I also have shown you how to maintain the code repositories. I've explained the difference between Git and GitHub. And I've also shown you how to push code into GitHub online repository. These are all additional things with respect to your data science solution development. All right, with this, we will conclude. Yeah, these things are available on GitHub repository, guys. Please go to the GitHub repository website and you'll be able to see all these things. It's given there. I've not created anything fancy here. Okay. GitHub documentation would be there. You can go through the documentation and get all this information. Just search for GitHub documentation. That's all. All right. So with this, we will conclude the masterclass for today. And we will connect again in the next masterclass. The constant efforts here that we are putting is to ensure that you understand the world of data science and different things that are required for implementing a successful project. Hope you have learned something new. These sessions will be repetitive. So any of your friends, or if you also have to drop out in between or did not attend completely, then you can also connect with us in the next session of the same topic, and we will do the revision of these things. All right, so until we will meet again in the masterclass, thank you so much and enjoy the rest of the Sunday evening. Thank you, friends. Take care.